Hi, my name's Russ. This is another video in a series that are being performed and presented to understand the fire forensic elements in NFPA 921. This particular video concentrates on how light bulbs and windows can be used in helping to understand the nature of a fire, how hot it was, potentially isolate its origin. Framed windows can have a 70-degree Celsius temperature gradient between the edge or the side of the glass and the center of the glass. And a lot of that has to do with how the edge is protected. So if you have an edge protected window, that gradient is going to be a little bit more severe than a non-edge protected. What I mean by that is if you have a framed window, you'll have up to a 70-degree Celsius temperature gradient. If it's unframed, it won't be that high because you have more heat transfer on the edges. So double layers are going to withstand significantly more flux heat exposure than single pane glass. You can roughly have a 100-degree Celsius difference in temperature for double layer glass before failing than single layer when exposed to a particular hot gas. One thing to keep in mind are vinyl window frames. They will melt, and what happens when your vinyl frame melts, the glass will fall out, and that will create a ventilation path for new air to come into a compartment. But technically, the vinyl frames will actually fail before the glass fails. Now, it's not the case in wood and aluminum. Aluminum is going to last longer, depending on what type of wood and how thick it is. Wood will last longer as well than the glass. In other words, the glass will break, potentially fall out before the frames will fail. A lot of vinyl siding's in place in new residential construction. This is a fairly common element in homes today. So what you can expect in fire conditions is that vinyl is going to melt, window is going to fall out. It's going to create more ventilation flow and result in hotter fires in a shorter amount of time than other ones. Overpressurization, sometimes people think that fires themselves will cause windows to break and fall out through overpressurization. It's not the case. Typically, you need about 2 to 7 kilopascals. I think there's 101 kilopascals in an atmosphere. So it gives you a feel. It's a very small amount of pressure, basically 2% of our atmospheric pressure. That's when windows will fail within a compartment. But when you're dealing with the typical flashover fire, you're only dealing with very small pressure differentials of about 0.01 to 0.03 kilopascal. Now, with that said, if you have a sudden introduction of oxygen to a ventilated controlled fire, you're going to have a backdraft. That's going to be kind of an explosive combination, hot pressurized gases hitting that window. That's going to cause that glass to erupt. So, tempered glass is exceptional. It's recommended in the Wildland Urban Interface Standards for exterior glazing, or have those windows focused on areas where you could have wildland fire occurrences. It can typically handle 4 times more pressure than regular glass. It's going to break into small pieces that are safer than typical glass, and that's why tempered glass is located in areas where safety is a concern. It is a requirement, I believe, in the International Code Council's Wildland Urban Interface Code for wildland urban areas with extreme fire hazard. Here's 2 examples of different types of cracking. Now, the one on the left, the cobweb pattern, that's an impact crack, whereas the one on the right, that is actually heat stress related crack. So, sit-on windows. In the past, years past, testimony has been given by arson investigators that have stated that sit-on windows is a telltale sign of ignitable liquids. And the scientific analyses has proven that just not to be the case. You can have no soot depending on how rapid the increase of the fire is, preceding breakage. You could have no soot in a variety of factors, and you could have lots of soot depending on your factors. So stating that ignitable liquids cause soot on windows is false. So don't believe that testimony. There's problems with it. Another myth that has been testified in court in the past is that crazed glass, it's caused by accelerants, ignitable liquids. And I think Lentini, he was a fire engineer. He did this experiment where he shot glass that had been heated up with a hose and wrote his name on it, or his initials. Now he did that simply to demonstrate that it's actually rapid cooling that causes this effect. And what crazing is it's not full penetration necessarily, but what it is it's basically surface cracking that runs in a variety of directions, and it leaves the glass to look like in the image. It's not an indicator of accelerants. So if anybody testifies to that, it's not the case. It's rapid cooling that causes that. Factors that limit conclusions. So what were the conditions of glass before the fire? Were they previously broken? You need to do some analysis with witness testimony to understand that. Thickness of glass has a significant bearing in terms of how fast the glass is going to break, how fast it's going to crack. The rate of heating. The rate of heating does play a factor. Overall temperature extremes do play a temperature. You're going to see cracking for typical single pane windows, under 500 degrees Celsius. It's very common. It's going to happen reasonably quick, and there's a dependency on acceleration of that fire, that heat applied to that surface. The frame insulation, or the type of frame used, provides a certain amount of insulation. That insulation causes the edges to retain, or to they can't release energy as fast, so it becomes an uneven heat distribution in the glass. So frames, the amount of insulation in that frames will result in temperature differentials in the glass that will result in accelerated cracking. Suppression activities and cooling effects will damage windows, so that needs to be taken into consideration as well. Quickly, let's take a look at it in light bulbs. There's 3 different light bulbs we'll look at. The first one, historically, incandescent light bulbs were used to basically point to not a fire origin, but where higher energy is coming from. If you look at the image on the right, and what happens is when it ruptures like this, even though it's under a vacuum, it's pointing in the direction where the fire is coming from. Similarly, you can see this pull effect in the image on the left, likewise showing that the fire is on the right side. It's deforming that that metal, or excuse me, the glass in the light bulb, and resulting in some plastic behavior. This is a helical compact fluorescent light bulb. Now what you can see, the fire would have been on the left side moving to the right, but there is a shadow effect. That'll help you narrow down which way the fire is going. So if you take a look on the right side of the fixture, you can see a shadowing from the light bulb that occurred. You can also see some soot deposited on the left side of the remnants of the bulb, and that also is an indicator that you had some fire coming from the left. This is an LED. LEDs are not under pressure like other bulbs. They're at ambient pressures, so they don't behave similar to like an incandescent bulb. But you still can take advantage of the shadow effect. That's going to be a part of light fixtures. You can tell where the fire came from light bulbs. So more modern light bulbs will often melt or be destroyed in a fire. Although that's the case, so in other words, LED lights are more likely to be destroyed than incandescent lights. You can still gather information from the shadow effect and from the soot deposition. The shadow effects, tails, and charring can be utilized to help provide insight to fire's growth and direction. CFL and LEDs will melt at lower temperatures than traditional incandescent light bulbs. And investigators should understand these effects as incandescent bulbs continue to phase out for the more popular CFLs and LEDs. So there's a 2007 law that was passed by Congress, by our government, that basically focused on more energy improvement. So that's why we've had this huge focus on better light bulbs that evolved into LEDs today. So what you can predict is the old-fashioned incandescent light bulbs that produce enormous amounts of wasted infrared energy, they're going to be phased out. So what we're going to be dealing with in the future are LEDs. And to give you perspective, LEDs actually are significantly more efficient than CFLs, and CFLs are significantly more efficient than incandescent bulbs. So we're going to see more focus on LEDs as the time goes on. The former two are going to be discontinued. So LEDs, the thing to take away from the LEDs, you really don't, because of the lack of pressurization in the bulbs, you just don't have the telltale signs that you're going to have on the incandescent bulbs. So you have to rely more on, like I said, the shadow effect and staining. In any event, I appreciate you taking the time to watch this discussion, and I hope you have a great day. Thank you.